Okay, hi guys, so we'll be continuing on seeing more on the relationship of Gibbs energy with entropy and the variation of the same with volume and pressure. So in the previous lecture we saw that dg was equals to vdp minus sdt. This was the relationship we got, and let's see what happens in case for chemical reactions or phase change. For chemical reactions or phase change, we can write that here we are talking about constant temperature. So just a thing before continuing forward, so we can write that d of delta g, or rather directly writing d of g would be equals to, as we are talking about constant temperature, so sdt term would vanish, so we have integration of vdp. Okay, so if we have v of delta g now, what we will have, d of delta g would be nothing but delta v dp. So now when we integrate it, we would have delta g2 minus delta g1 would be equals to delta v p2 minus p1, where delta g is the Gibbs change in Gibbs energy at pressure p1, delta g1 is change in Gibbs energy at p1, and delta g2 is change in Gibbs energy at p2. Okay, so from x of s to x of l, we are talking about the phase change. So if we take 1 mole of x of s, which is getting converted into x of l, we can write delta v would be equals to v of m x comma l minus v of m x comma s. V of m is nothing but the molar volume. We already know that delta g rather would be equals to vdp minus sdt. And a concrete example of the same could be, of a phase change, could be carbon in graphite form gets converted into carbon in diamond form. Okay, so delta v would in this case would be molar volume of carbon in diamond form and molar volume of carbon in graphite form. Okay, so now let's take a look at what happens at constant pressure. Okay, so at constant pressure we can write that dp is 0, so we can write dg would be equals to, as dp is 0, we can write dg would be equals to minus s dt. Okay, so this is dg, not delta g. Okay, so or we can write that del g upon del t at constant pressure is equals to minus s. Okay, now we can write that for a particular substance in solid, liquid or gaseous form, which is in solid, liquid or gaseous form, we can write that s dg is equals to minus s dt. We can write, or rather we can integrate both the sides, and we can have delta g would be equals to minus s delta t. So at constant pressure we'd have graph something like graph of g versus temperature would be varying like this. So this would be for gaseous phase, this would be for liquid, and this would be for solid phase. Okay, the graph would be negative in slope because of a minus sign present over here. Okay, so now let us see what happens for chemical reactions and phase change when we have d of delta Rg, that would be equals to minus of delta Rs dt. Okay, so this we are seeing the case for chemical reactions or phase change at constant pressure. Okay, so we can write that delta Rg2 minus delta Rg1 would be equals to minus delta Rs T2 minus T1, where delta G1 is change in Gibbs energy at temperature T1. We are just using the analogy which we have already seen for chemical reactions or phase change at constant pressure. So from the same we can get the inspiration that delta G1 would be change in Gibbs energy at temperature T1. Okay, and delta G2 would be equals to change in Gibbs energy at T2. Okay, so for the next topic is for reversible reactions of the type A moles of A plus B moles of B getting converted into C moles of C and D moles of D. So we can write that for reversible reactions of the type AA plus B of B getting converted into C of C plus D of D, we can write that at constant temperature and pressure delta Rg would be equals to delta Rg naught plus Pt ln Q, where Q is the reaction quotient. Okay, and as per thermodynamics, we would have Q as A to the power AC to the power C, which is nothing but the activity of C to the power C, AD to the power D divided by AA to the power A and AB to the power BB. And for an ideal gas, we can see that AI is equals to partial pressure of A divided by P naught, which is the standard pressure. Okay, so P naught is the standard pressure. Which is equals to 1 bar. Okay, and for solutes or ions present in solution, we can write that AI would be equals to Ci upon C naught, where C naught is the standard concentration, which is equals to 1 m. So with this we come to the end of this lecture. Okay, but one more thing before ending, that for solutes, or rather not solutes, for solids, or rather solids oblique pure liquids or solvents, AI would be equals to 1. Okay, so with this we come to the end of this lecture. In the next lecture we'll be continuing on seeing more on the thermodynamics of reversible reactions. So till then, good luck and goodbye.